Hey everybody, this is Mr. Beckstrom, and today I'm going to go ahead and go over a few problems from sections 7.3 and 7.4, and this will be kind of a replacement class for the Wednesday, November 25th class, because I know a lot of you are going to be out of town or doing other things since this is Thanksgiving week. So feel free to watch this class at your leisure. I'll count this class as well for attendance, and I'll be checking this just to make sure that you've looked at it by Tuesday. That will be Tuesday, the December 1st. So you'll get credit for being here as long as you watch the video by then. All right, so the first problem I want to take a look at is similar to 7-3. This is the second problem. It says monthly payments of $75 are paid into an annuity beginning on January 31st with an annual yearly interest rate of 3% compounded monthly. Add the future values of each payment to calculate the total value of the annuity on September 1st. So what they want us to kind of do is they want us to take a look at each month's payment and kind of add them up and see what the value of that annuity is going to be on September 1st. So we're going to have 8 months worth of payments. That's going to be January through August. And let's take a look at that. So the first thing I want to do is, and I can use this front. Oops. Do that. So let's go ahead and type the months out here. So I'll do January, February, March, April, May, June, July, and August. All right, so I'll put that right here. And then what I want to do is I want to see, so the January payment, that's going to accumulate for February, March, April, May, June, July, and August. So that's going to accumulate for 7 months. So I'm going to use that my compound interest formula for 7 periods. So if you remember, our compound interest formula looks like this. It is what? The principal, right? Times 1 plus R over M raised to the N. So this is my rate. This is the number of annual payments, and this is the total number of payments here. This is my principal there. All right, so if I'm using this formula here, since we're talking about compounding interest rates, looks like I'm paying $75 each month. So for January, I'm going to have $75 that I put in, and I'm looking at 1 plus my rate, which is 0.03. That's my interest rate. Over, I have 12. This is monthly, so that's 12 times per year. Over, and we said that it's going to be counted 7 times, so raised to the 7th power. And then let's go ahead and just do all the rest of these. Now, before I go any farther here, let's go ahead and see what 0.03 over 12 is. So 0.03 divided by 12 is equal to 0.0025. If I add that to 1, I'm going to get 1.0025, and I'm going to use that calculation in all of these, but I'm going to raise them to different powers here because the February is only going to be counted 6 times, the March only be counted 5 times. So I'm going to go ahead and store that 1.0025 as X. So I'm going to store that, hit the store as X key, so I can easily just pull that up when I'm doing my calculations. So let's go ahead and write the rest of these, and I'm just going to, instead of doing this whole thing is just 1.0025. So February is going to be 75 This is going to be 1.0025. This will be raised to the 6th. And then we can just kind of see that quotation, quotation, raised to the 5th. And then all the way down here, quotation, quotation, and this one is raised to the 0, the last one, right? So we go, because we have 8 of these, so we're going all the way from 7, and then there's nothing below this, so this is raised to the 0. So now let's go ahead and count all of these up. So 1, 2, 3, 4, 5, 6, 7, 8. We should have 8 of these all together. And I'll do the first couple, and then I'll let you do the rest of them. So the first one is just going to be 1.0025, which I stored as my x. So I'm going to say x raised to the 7th, enter, times 75. So this first one is going to be 76.32, 76.32. My next one is going to be that 1.0025, so x raised to the 6th power, and I can just multiply that by my 75, and that's 76.13, 76.13. Y'all can do the rest of those, and then the last one is going to be 1.0025 raised to the 0th power, which is just 1. Anything other than 0 raised to the 0th power is just 1. And then 1 times 75 is just going to be 75. And you're going to add all of those up. I'm not going to do all the middle ones for you. You can do those. But I will tell you, I think I did do the final answer, and it should come, this one should come out to 605.27 if you want to check your answer. All right, and if you have any questions on that one, let me know. All right, so now let's take a look at the next one. Okay, so for this next one, let's do one of these ordinary annuity problems. It says, find the value of the ordinary annuity at the end of the indicated time period. The payment R, the frequency of deposits M, which is the same as the frequency of the compounding. Remember, in order to do one of these, those have to match or we can't use this formula. The annual interest rate R and the time T are given below. All right, so the amount, so it's $700 monthly, 3% interest for 3 years. All right, so let's first go ahead this time, and we're going to go ahead and identify all of our notation. So the monthly payment, that's equal to $700. According to that, our interest rate is in decimal form is 3%, so 0.03. Our M, that's the number of periods per year, is monthly, so that's 12. Our N, the total number of periods is, remember, we can find that out by taking M times T, which in this case would be 12 times 3, which is 36. All right, and then it's really useful in these kind of problems to go ahead and identify our R over M, because we use that in multiple places. So that's, in this case, 0.03 divided by 12, which I can pull up my calculator, and 0.03 divided by 12 is 0.0025. So 0.0025. And we can, as long as it's not a repeating decimal, I can go ahead and substitute that in wherever I see a R over M. And in fact, since it's a 1, that's just 1.0025 there. All right, so let's put all that into the formula, and then we'll put it into our calculator. So A, which is what we're trying to solve for, is equal to the capital R, which is the monthly amount there, so 700 times 1 plus R over M. That's just going to be 1.0025 because it's just 1 plus 0.0025. So 1.0025 raised to the 36th power minus 1, right, all over 0.0025. 0.0025. All right, then I'm going to pull up the calculator here. So I'm going to do, remember, we do the inside here first. So I'm going to do 0.0025. Oh, 1.0025 raised to the 36th power. All right, enter. Minus 1. Enter. We complete the numerator, and then I'm going to divide by 0.0025. Then finally, I'm going to multiply by 700. Enter, and I get $26,334.39, and that is my correct answer. All right. If you have any questions about that one, let me know. And now let's move on to the next one. All right. Here's a problem here that is much more of an algebraic problem, but it's one that is important because it teaches us how to use the logarithmic equations and specifically the natural log. And we will need to use this when we have variables in our exponents to get them out of our exponents and to be able to work those kind of problems. So this here says solve the equation for x, and it gives us something crazy like this. So the strategy for solving one of these is to get the term, that's the 7 raised to the x by itself, and then use natural logs, to use the rules with natural logs in order to get the x out of the exponent form and then to solve for x. So let me kind of show you how to do this. So for a problem like this, the first thing we want to do is isolate this term 7 to the x. So I can multiply both sides by 8. So let me go ahead and write this down. So I have 7 raised to the x minus 8 all over 8 is equal to 21. So if I multiply both sides by 8, that will cancel out those, and I'm going to get 7 raised to the x minus 8 is equal to 21 times 8, which is, clear that out, 21 times 8, 1 times 8, which is 168, which is equal to 168. Now I can add 8 to both sides, and I'm going to get 7 raised to the x is equal to 176. Now that I have this term with x isolated, what I can do is I can take the log of both sides. Now you can take the log of any base to both sides. So I can take the log base 10 to both sides. I can take the log base 2 to both sides. I can take the natural log to both sides. Remember, the natural log is the log base e. That's the log with this base to both sides. The log base e is shortcut, or it's abbreviated as ln, which we call the natural log. So these are both the same thing. So when you hear the natural log, it's just a log with this base e. E is an irrational number. That's 2.718 something goes on forever. The reason that we either use log base 10 or the natural log is because those are the two logs that our calculators use. Here's the log base 10 key right here, and the natural log key is right here. Our calculator doesn't actually use any other logs with any other bases, so it's best to use one of those two. I like to use a natural log just because, I don't know, it's quicker. So the reason that we like to use the logs, because there's a nice rule. And it says that if you have a log with any base of something raised to a power, so if you have a log with any base, doesn't matter what it is, of something raised to a power, that you can take that power and bring it out front and bring it right out front. So you can take the power and bring it out front and multiply it by that log. So it's a really nice property. You can take the exponent and bring it out front of that log to multiply. So that's why we like logs so much, because we can do weird things that we can't do with other types of functions. So one thing I can do to both sides, just like you can add or subtract or multiply both sides by something, is I can take the natural log of both sides, or I can take the log base 10. But in this case, I'm going to take the natural log of both sides. So I'm going to take the natural log of 7 raised to the x is equal to the natural log of 176. And so this doesn't change the value of my x. I can still do this to both sides. Now I'm in this form here, and that means I can take the x and I can put it out front. So now x times the natural log of 7 is equal to the natural log of 176. And now, remember, the natural log of 7 and the natural log of 176 are just values. We can put them on our calculator, and there's some decimals. Now I can divide by those values from both sides to get x by itself. Oh, wrong. Divide both sides by natural log of 7. So x, I can just cancel out those two values, is equal to the natural log of 176 over the natural log of 7. This is definitely going to be some kind of irrational number. Let's go out 4 decimal places because that's what my math lab is asking. So if I do that, I'm going to say the natural log of 176 divided by the natural log of 7. And that's going to equal 2.6571. 2.6571. And that is your final answer. All right, so this question here is from section 7.4, and it says, given the annual interest rate in a line of an amortization schedule for that loan, complete the next line of the schedule. Assume that payments are made monthly. So they want us to figure out the next payment, the next amount of interest paid, the next paid on principal, and the next balance line. So remember, this is something that we're paying off. So our interest rate will stay the same. Our payment will stay the same because we're making the same payment every month. The amount of interest we paid should go down a little bit because this is how these loans work. Usually with like when we purchase a house, we usually start off with a high amount of interest that we're paying each month, and then it goes lower and lower and lower. So it should be a little bit more than that. The amount of principal that we pay, that's like the actual amount of the loan that we're paying back, should be going up a little bit. And then the balance of the amount of the allowance of the loan should be going down. So let's kind of figure out how we go about doing this. So what we want to do is we want to figure out, first of all, well, we know what the payment is going to be because it's going to be the same payment each month. So let's write this in. So under the payment line, we're going to do 476.05 again. So 476.05. So that'll be on the next. There should be a period right there. All right. So under the interest paid, we got to figure out how much interest we're going to be is going to be portioned on this. So to figure that out, we're going to take that annual interest rate of the 8.8%, and I'm going to do this off to the side over here. So that's going to be, I'm going to divide that by 100 to get that decimal. So that's 0.088, right? 2, and divide that by 12 in order to get the annual interest rate to a monthly interest rate because we're doing that monthly. And let's see what that comes out to. So that's from the last problem. So 0.088 divided by 12. And we get 0.00733. And I'm actually going to leave that in there like that because I'm going to end up using that. And then we're going to figure out the interest using the simple interest formula, which is just PRT. We should be familiar with that. So the principal, it's going to be based off of this amount here. So that's 7162.12. That's the remaining amount left that we're buying, times our rate, which is that amount, what was that? 0.007 with repeating threes, 0.00733 repeating here. So I'm just going to write a little arrow up there, times that, times the time in years. This is an annual, so we're just going to do times 1. So it's really just this times this. So I'm going to go up here, and if I just hit the times key, it'll use my last answer, so I don't have to type that whole thing again. And I'm just going to multiply it times the new balance there, times 7162.12. So this will be the amount of interest I'm paying this next month, which is $52.52. So this is the new payment. My new interest is $52.52, which makes sense because it should be just a little bit less than the interest I paid the month before, right? So the amount that I'm paying on principal, remember this is my payment, this is the amount that I paid on interest. So the remaining amount, so if I take the 476.05 and I subtract that 52.52, the 476.05, so all the rest of that, the 423.53, so the 423.53. Remember, we said the amount that we pay on principal should be going up. That's the amount that I paid that's actually decreasing the loan. And then my balance, that principal balance, should be going down by this amount right here. So I just subtract this balance by this amount here. So I do 7162.12 minus that 423.53, 423.53, and I get 6738.59. 6738.59. And that's it. And that's how you get the next line of an amortization schedule. All right, let's move on. All right, here we have a decently easy problem to kind of go in some of these tougher ones. It says here you take out a 7-year amortized loan to buy a new car after making monthly payments of $247.70 for 4 years. You still owe $8,407. If you decide to pay off the loan, how much will you save in interest? All right, it looks a little tricky at first, but it's really not too bad. So you take out a 7-year loan. So after 4 years, you still owe this much left. That means you still have 3 years to pay, and you're paying monthly. So you still have 3 years monthly, which is 12 times 3, which is 36 payments left. So 36 payments at $247.70 per payment. We can easily find out how much money that would be just sticking it into our calculator. So if we were to pay this off over the next 3 years, it would be 36 more payments times 247.7. That would be $8,917.20. 8917. 8917.20. 20 cents. So that's how much it would cost if we wanted to just continue making our monthly payments for the next 3 years. Now let's say we wanted to pay it off for the 8407, right? We could do that as well, 8407. How much would we save if we just paid it off? Well, it's a simple subtraction problem, so let's just subtract that 8407. We would save $510.20. So and that is your answer, $510.20. So nice, easy one in there. There's not a lot of formulas, just a little bit of common sense. All right, let's get one more of these out of the way before I let you go for your break here. All right, how's everybody doing here? So this is the last problem, and here's one of the biggest formulas that we're going to have to deal with in the entire class. All right, so this one here is given a loan amount P and an annual interest rate R and the length of the loan in years. Find the monthly payment, capital R, necessary to pay off the loan by completing parts A through C. Represent the number of monthly payments by N. So they're giving us this. I'm going to kind of let you know how they're doing the A through C parts just on my board here. But this is basically what they're doing. So here's the whole formula. I'm going to write it out, and I'm going to let you know what they're doing. So the main formula looks like this. It looks like P. So the left side of it looks like our generic compounding interest formula, R over M raised to the N. And then our right side is like R times that annuity thing, and it's like the 1 plus R over M raised to the N minus 1 all over, should be an R by the way, all over R over M. And we've worked with this formula over here, we've worked with this formula over here, and so what we're solving for here is the capital R. This is what we're solving for in the problem. So what they're wanting us to do is they're wanting us to treat this whole thing here as A. This entire thing, except for that capital R, as B, right? So if we find this value here, and then we find this value, and then if you just divide this entire side by B, then R here is really just A divided by B, right? Because R is just going to be this side divided by this side. So that's what we're going to do. First, we're going to find A, and then we're going to find out whatever value this B is here, and then we're just going to divide A by B, and that'll be our R. So that's our process here. So A is going to be equal to our principal, right? Now that's this one right here, our principal, 80,000. 80,000 times 1 plus our rate, 0.07, divided by our number of periods per year. It's monthly, so divided by 12, raised to the 12 times 15, right? The total number of periods, 12 times 15, which is 180. So 180. So let's put that in our calculator. So I'm going to have, and I can put this all in at once if I want to. So I can do 80,000 times 1 plus 0.07 divided by 12 raised to the 180. And I get this big number here. So that is going to be, so A is equal to 227.915, not point, comma, 915. And I'm going to go out a couple of more decimal points than normal because we are in the middle of a formula. I only round when I get to the end of a formula. Now for B, let's put this in. That's going to be this side except for the R. So we're going to have 1 plus r 0.07 over m, which is 12, raised to the n, which is 180, minus 1, all over r over m, 0.07 divided by 12. All right, so let's figure out what this value is here. So B is equal to, and this one, just to give you a little different, I'm going to work this one out step by step. So I'm going to do 1 plus 0.07 divided by 12. Make sure I do it in the correct order of operations. I'm going to raise that to the 180 power. I am then going to subtract 1. And finally, I'm going to divide that by this. Don't forget to put that in parentheses to make sure it does it in the correct order of operations. 0.007 divided by 12, like this. And that one, I'm going to get, I put that in wrong. So let me go back and redo that one. Sorry. 1 plus 0.07 divided by 12. Enter. Raised to the 180. Enter. Minus 1. Enter. I put 0.007 instead of 0.07. Divided by 0.07 divided by 12. Not that. 316. So B is equal to 316.96, and I'll put a couple more decimal places in there. 22967. 967. So now I can just divide both sides by this B. So R is going to be equal to A divided by B, right? Because I can just divide both sides by B. So it's going to be equal to this divided by this. So let's go ahead and do that. So it's going to be this thing. So it's going to be 227.915.7385 divided by B, which was my last answer there. So I can just do second answer. That'll pull up my last answer. And I get 719.06. So 719.06. And that, my friends, is my final answer. 719.06. All right, I hope this helped. I got through at least 3 problems from each section. So try them out. Try some other ones. Let me know where you're having trouble, and we'll go from there. This is it. This is the last section. So from here on out, we got the slow quiz, one more test, and the final exam. So it's been real. It's been good. But it ain't been real good. No, I'm just kidding. I've had a blast. All right. Let me know if you have any questions. Thanks, y'all.